So, hello. The next talk is going to be about embedded system reverse engineering. The speakers are going to be Nathan and Vadik. Without further ado, the stage is yours.
Okay. Thank you very much. Any questions? Okay, so we're giving a talk on embedded analysis. We were contemplating what to call this talk. And considering that you guys are getting so old, I mean, you have a daycare here now, next is going to be bingo instead of go, we thought this one would be good, which is pretty much your kids can do what we're about ready to describe. And we're curious why you software hackers aren't doing this. So instead, we stuck with something more pragmatic. And that's basically the premise of this talk is there might be a lot of hardware engineers in here, and I promise you, I am the stupidest among you. I would consider every other electrical engineer in this room to be much smarter than me. And that's why I'm giving this talk, because a lot of you aren't hardware engineers, and this should be a good intro for you to start hacking away at hardware and embedded devices. First, we did write up all the details, especially all the technical details of this talk are covered at this particular wiki page. So if anyone is listening, or if anyone is on video and wants to follow or doesn't have the slides, you can go to eventsccc.de/congress/2010/wiki/embedded_analysis, and you can follow along the technical stuff. What we're going to cover are a bunch of tools for simplifying embedded analysis. So let me start by saying that it's either that embedded analysis and hardware, the field is extremely stupid, or I'm extremely stupid. And if it's me, how I overcome my stupidity is by developing tools to help me, be a bit smarter. So one of the tools is RS-232 which basically, when you have a set of pins inside your device, or pads, or vias, and you want to determine if serial is enabled, this is a tool which we'll go over that makes this easier. Another one is finding JTAG amongst that set of pins. Another one is dumping flash parallel specifically, so an easy way to use an Arduino to do this. We're going to go over some techniques for redocumenting undocumented chips. Vadik is going to present DPCB, which is for analyzing and reverse engineering the traces along a PCB. And then we're going to look at the human elements, some other sort of interesting notes from my work and looking at embedded devices you might take notice of. Why do embedded hacking, just as a quick intro? So people might do this for homebrew, that's probably, or piracy, or security, that's probably what most people here are familiar with. And you might be familiar with some of the projects that are listed here. But there's also another field that I would like you to look at, which is artistic reuse. I sort of studied 2 years at Fachhochschule Potsdam in Potsdam, interface design, physical computing, and this is also an interesting field to apply your skills. So just quickly, some examples of why you would open the device. This is a set-top box. It's a DirecTV set-top box. Someone makes a particular board that you can install. You can see it here, it's highlighted. This board they show you how to solder the points on the board between the decoder and at some point after it's encrypted, but before it's completely decoded from MPEG into whatever, NTSC, whatever. So then this board will then give you a FireWire port that you can then record the MPEG stream out to a FireWire or VCR or something like this. So they sell this for $150, and they give you the directions for exactly where on the PCB you need to solder this board into in order to tap on the bus. So that's an interesting example. Artistically, I'll give you an example from my school. I'm really sorry, I have to switch between slides and videos a lot. So give me 1 second. Just to show you this stuff. So this is, at my school, a lot of people that come have very little technical expertise, but in the very first week they're asked to take apart a keyboard and make some interesting application. And so basically reuse a keyboard. And after that first week, they present their wares, and this is one of them. I just wanted to show a couple examples. And these people have very little technical expertise. here. So she made a nice interactive flash kicking game with a keyboard. Or there's another guy that made a sort of Guitar Hero. So again, so what has made this much easier for people is in part due to Arduino, which we're going to discuss, and it's also being discussed in other talks at the CCC. So these tools are what we use in this school to introduce people with very little technical expertise into sensors and hardware hacking and stuff like this. Another topic, I'll skip that one. Another topic which is closer to me is something I did with David Bortz at the Bezalel Academy of Arts in Jerusalem. And he wanted to create this model where it would sort of fluctuate, these SMA alloys would fluctuate based on your heart rate. In Israel, it was kind of hard to get a hold of the electronics and different components to build one, and we were short on time. So we took apart an existing on the market pulse detector, pulse multimeter, I don't know, sorry. And so we spliced it open, and over here on the top right, you can see a microcontroller. It's very similar to an Arduino, and this is connected into a point where we can get the pulse coming out of the heart rate monitor. And the result is pretty nice. I'll show you real quick. This video site really stinks. Oh my gosh, okay. Really bad pixel. But so this is being influenced by his heart rate in the shirt itself. So again, that's another example where we had to reverse engineer some market device for reuse, and that's what I wanted to try to emphasize. So it's not just hackers that could use your skills. You might find a local art school that is also interested in talking to you. So those are the examples. There's two things you're going to get in this talk. One is an understanding of tools that will make it much easier for you to do embedded analysis, and the other is the human element, where you can start to try to notice the engineer that's involved with the design, because this gives you some clues as to demarcation points that can be interesting to look at. And I like to use this. It's from Joel on Software. He was talking about the law of leaky abstractions, and he was applying this to software engineering, where you have different languages which are in their own abstraction layer, and the moment that you go to university, you learn all these different abstractions, and then the moment you get out, you have to do what programmers actually do, which is debug the abstraction layers. So he wrote this up very nicely and calls it the law of leaky abstractions, but it applies just as well to hardware analysis. In particular, when I talk about the human element or the human abstraction, I'm looking at the different types of engineers that are involved. So you might have chip designers that design the ASIC. You have PCB designers that deal with the layout of the little green board, and then you have the actual embedded software developers. So each of these might require different interfaces, and that's a lot of what we're going to be looking at. So an example of a leaky abstraction. So here is a nice chip on some board. There's some epoxy sitting on top. The epoxy is meant to make it hard for you to touch the pins and tap them, or to desolder and remove this particular chip. I guess it stores some secrets, but the problem is on the bottom of this board, all of the vias are exposed. And you can imagine there's probably a chassis spec or some sort of security specification, and because of the different types of engineers involved, it's a bit difficult to get the full scope of what measures might become mute because of something like this. So it's a bit difficult, and you'll find lots of interesting demarcation points. So again, that's the human rule, this law of leaky abstractions. So first we're going to look at debug interfaces. And there's a bunch of them for different purposes. JTAG might be used to check the health of the connection between the solder joint of a chip. You might remember like the Xbox, I can't remember what it's called, the red box bug or something, which was just basically the FPGA sort of got desoldered slightly, or a few of the pins, and then they had to, it affected like 20% of the Xboxes. So you might use JTAG to check for something like that. You'll check the connection between different ICs to be sure that the trace on the PCB is healthy. You'll check the actual state of the pins on the chip with JTAG, or you might use it to program memory. You can also use CFI, parallel programming, serial. You'll use serial I2C to communicate with sensors, and perhaps I'm missing some stuff. And you might use JTAG and serial to debug the actual processor. So these are the different debug interfaces that I'm looking at. And so let's take the first, which is serial. So with serial, with all of these, I like to look at the electrical characteristics of the actual pins when I'm looking at a device and I have a set of, let's say, 40 pins. I would like to reduce the set a bit so that I don't have to check them all. So it can sometimes be helpful to check the voltage or resistance and things like this. With serial, you have some characteristics. So if you see a 3.3 volt line or 12 volt or 5 volt, these could indicate serial. They're not exclusively indicating serial, especially 3.3, which is very common for TTL. But they could give you a certain point to start focusing on when you're looking at the different pins and vias. I just want to note that most of the time when you think about serial on an embedded device, you probably think about the console on your router, how you can just sort of plug up and then get a shell. But there's also other interesting types of serial interfaces. This is one that's for a CPU, where you can actually program the internal memory using serial and your normal X modem protocol and all that stuff. So you might find other stuff. So how do we find it? Well, there's the hard way, which is for each pin in your target set, you will attach an oscilloscope to the pin and then look for data patterns and maybe restart the device thereafter. And this is a print from an oscilloscope on two serial lines. So the console must print, for this test to actually work, the console must print when you print something it must output some sort of serial data when you start up the device. Another hard way, if that's not the case, or if the situation is different, for each pin on the target, for each baud rate that is possible, then connect your board, such as this one, a serial board. Then you connect the board to that pin with that baud rate and check the line to see if you're getting some data into your computer. So you open the workstation, etc. Wait 10 seconds, restart, and stuff like that. This doesn't work if the target requires stimulation, so sometimes you'll need to send a carriage return or press enter in order for it to give you some sort of meaningful output. So that doesn't work here. And to modify that, you would have to add another for loop to check each of the TX pins. And basically, after you get halfway through this, you might commit suicide. I'm still living today, and the reason I'm living is because I developed a tool which allows you to plug up to all of the different pins. It scans for all the target pins at all possible baud rates with and without wake-up patterns, and it's Arduino-based, so it's very stupid. And that's basically what I want to show. One side note, whenever you're plugging up your electronics to your target, you need to be sure that your board speaks the same voltage level that your target board speaks. Arduinos in particular come commonly at 5 volts. So if you want to modify it for 3.3 volts, this is how you do it. You can install a voltage regulator. On the wiki page that I mentioned at the beginning, I have links to this and with annotations and whatnot. So yeah, that's an important note. So Arduino, I think it's probably better covered in another talk that's going to cover this, someone else is doing. But I just want to point out that originally it started from wiring, which was made at MIT. It's another prototyping board. And then some Italians came along and made Arduino, which was a completely open source sort of clone of it. And it's now used, I mean, I think most industrial design schools that I visit a lot of the students use Arduino. So it's a very simple IDE. It has a full C subset, but it's very well documented for a small basic subset of C. There's many clones that work with AVR and PIC, and there's excellent documentation. You'll find all sorts of interesting projects. I just wanted to show you a few that I found interesting. This is from someone, I think, here in Berlin. Let's see. All of these projects sort of started out with an Arduino, or I'm pretty sure. Oh, I have to load it. No, I won't do that. So I won't show you that one. It's basically an interface for a keyboard that sort of detects where your hand is and sends out MIDI signals. Another one is, oh my God. Sorry. Okay. So another one is, this is from ITP in New York. So it's sort of a device that has the same chip from the Arduino, and I'm pretty sure they developed it with an Arduino first, that you stick in your plant, and when your plant is hungry, it sends you a Twitter message, which hopefully goes to your cell phone and saying, I'm hungry, or you fed me too much. So there's all sorts of very simple things that are coming from different art students or designers or that start out with Arduinos. So here's some example output of a serial scan. There's 3 basic scans. One is passive parallel. It's basically like a logic analyzer, but a very slow one. So it just shows which pins change state. So if there was serial activity happening just on boot, then you should see a lot of activity on a particular pin. This particular output doesn't indicate a lot of activity over the period of 4 seconds. Another scan is active parallel. So in this case, it picks one of the pins to be TX, the SYN pin, and then it uses the rest as an RX, and then it waits a while. It tries each possible baud rate, and on the TX pin, it sends one of your wake-up signals that you define in software. In this case, it's 0A, which is, I think, a /n. There was nothing interesting in that one. Now it tries at another baud rate. There's nothing interesting. And now we get to 11520 baud rate, and we have a lot of activity on pin 27. So this probably indicates serial. In fact, it definitely indicates serial because the way in which the baud rate is sent is also using serial. So it probably wouldn't respond. Who knows? Anyway, at that point, you would probably take it and plug it up, those pins, pin 27 as your RX and pin 33 as your TX, to a serial cable, and hopefully you'll find serial. It also does another scan, which is active per pin, as opposed to polling the RX pins in parallel. It selects one and pulls each one individually for each combination. So I'm not sure that's useful, but it might be good for debugging. Yeah, so that's serial. So assuming, let's say, you didn't get something interesting, you weren't able to get to the code or dump the firmware or something like that, you might move on to JTAG. I'm going to explain JTAG really briefly, just so you understand what the pins are for. So we have 4 pins here. We have input, TDI, we have output, TDO, TCK, which is clock, and TMS, which controls the state of the tap controller. So we have a few registers as well. One of them is the identification register, which gives you the ID of this particular chip. And to try to explain why we have these different pins, I'll try to imagine we were developing this functionality ourselves. So if we wanted to get the ID register, we would probably have an output pin and a clock pin. So we would toggle a clock, check the output, and then it would shift a bit, this particular shift register, and then do this for 32 bits until we get the particular ID code. So that's how we would do it. So we would only need TCK and TDO. But when you deal with multiple registers, that's where the different pins become important. So with this particular pin, which is a boundary scan register, which allows you to check the state of all of the pins on the chip, as well as some internal registers. Here, again, you need, just to read the boundary scan register, you need the clock and the output. But also you can influence the state of those pins, so you can shift in bits to set a state on this particular chip on these pins, which might be useful for checking this, checking what happens with a chip that it's connected to see how they interrelate. So now we've added another pin. The TMS pin becomes important to be able to switch between these different registers, including switching into like higher level on-chip debugging modes and things like this. So this is why the TMS pin exists. And I won't get into how the tap controller works, but that's why we need these 4 pins. You also have a scenario where you can chain together various JTAG-enabled devices. So in this particular scenario, the device on the left is the tap controller set so that the boundary scan register is between input and output. And on the right, the bypass register is set between input and output. And this allows you to shift the boundary scan register totally through the chain and get it on the output, and allows you to chain the devices together. So that's something to be aware of. So again, the electrical characteristics when you're looking at these pins, let's say we're ready to try to find JTAG. Resistance, some of the pins, if you go back here, you'll notice that some of these have a pull-up resistor. It's the one there. So for those particular pins, you should find a pull-up resistor somewhere on the device. And the original specification, the example used 4.7K, even though it specifies it can be 1 to 10K, and in many cases, I do find that they use 4.7K. And so if you're looking around at different resistors on your PCB and you find some 4.7K resistors, that might be an interesting place to look, especially if you don't have any vias or pins around. Right. So now we plug up another tool, which is JTAG enum. Here it's being used by Jörg Albert on a Netgear router. He's trying to break the parental controls, and he's trying to check for JTAG. Here's some example outputs. So again, you plug up all your pins to your microcontroller, load this particular Arduino sketch on, and run S. And what it does in this particular case is it's scanning for a pattern. So it's assuming that the bypass register is the default state when you turn on the device. So now it tries to shift through a random pattern. If it gets that pattern on the output, it knows it has JTAG. So you can see here where it was found, and then it also detects the length of the instruction register, which can be important later. Another scan it will do, if that didn't work, is an ID code scan. Sometimes the ID code register is the default. And here you see an example of an LPC chip. This is the actual ID for an LPC chip that we checked. And that's basically what it does. There's another feature in it which enumerates through all the possible instruction registers, which can be useful for detecting hidden buses or potentially reverse engineering on-chip debugging functionality. This was discussed last year in detail by Felix Domke, and it's a great paper. You should read it. Some of this functionality is in JTAG enum, but also in the source repository, you'll find OpenOCD scripts, which basically replicate his work almost exactly, so that you can follow it and reverse engineer JTAG buses. So the future of this tool, and the reason I'm mentioning this is because we need some help. What I start to notice when I was enumerating the instruction registers is that I get a nice data set that gives me a pattern for what this chip is. It gives me a signature for it. So it might be useful for us to have a, let's say, public database where we can store such patterns and communal knowledge about it, so that if we have a chip that we cannot identify, or if we have a chip that we cannot find particular information about, we can use this signature to share knowledge. That's one place that we're possibly going. So that's JTAG. Assuming you didn't get access to JTAG, on-chip debugging, or ability to dump the memory over JTAG, the most brutal thing you can do is pull the chip out and just dump it. And this is an example. In this particular case, this was a chip that I was able to get documentation for, but finding a commercially available programmer to dump the memory was hard to find. Some of them required NDAs, some of them just took a lot of time, and sometimes you just don't have time. And they are expensive as well, whereas this only cost about 20 euro. So again, this is an Arduino clone up at the top, and I'll give you a link in a minute with the source code that you need to run. And on the left, you have a bunch of shift registers that attach to the address lines. And on the right, you have shift registers that attach to the data lines. And it basically shifts out the first address and reads the data. That's really simple. So what you need to be able to apply this to another flash chip is you need from the data sheet a list of the pins, so you know what are address and what are data and which pins are for state. And you also need timing information. This might look a bit scary, but actually if you remove all of the vertical lines and all of these minimum timings, T, R, C, T, A, C, what you're left with is that you need to pull the CE line down, then pull the OE line down, et cetera, et cetera. So it's just the order of the state pins that is important. So these are the two things that you want to find from a data sheet of your target. And once you have that, you can basically modify the code to dump the memory of your target. I should also mention that flashrom.org has a whole infrastructure. I don't think they deal with parallel flash, but they do deal with like NAND and stuff like this. So they also have some support for microcontrollers to dump memory. So there should be no reason that you need to buy a programmer, an expensive programmer. You should be able to dump it on your own. One of the things that I used in developing this particular tool was fritzing, which is developed at Fachhochschule Potsdam. It's a sort of breadboarding application that allows you to lay out all of your components. This wasn't where this was useful for me was for debugging, so when I had a problem I could come back and check if what I'd actually placed on the breadboard and how I'd arranged it was how I'd originally designed it. So a small side note about fritzing. It gives you schematic output, so you could actually take that and ship it off to China and have a PCB made for you. It's also really cool because they have this whole network for sharing. I'll show you the application real quick. 1 second. Right, so this is the same layout. So you can see here we have a schematic view, and then you can also lay out things on a particular PCB and then ship this off. You can export it, and then you can also share this with other people, and this is a good way to learn a bit about hardware prototyping. So here is, for instance, a very early version of the flash dumper, which I shared. And here are a bunch of other projects that people have made. Some of them are just fun and interesting, and some are not. So, right. So how do you actually get this chip out of the device? I didn't load this. Hopefully it loads. 1 second. Sorry. Show you real quick. Here. Okay. So removing the chip is a lot easier than it seems. Oh, Firefox. Sorry. All you need is a soldering iron and solder and some solder wick, perhaps, to remove the solder and clean it. Okay. Great. Okay, so basically I've applied a bunch of solder to one edge. What this allows is once the solder is evenly applied across all of the pins, then applying heat to one point makes all the solder fluid, so that allows you to pick it up. So at some point I just apply heat and start to apply just a small amount of pressure underneath, and then it sort of pops up. That's it. So you do this to both sides, and then you clean it with solder wick at the end, and then you're done. So it's not that difficult. So those are basically the tools that I've been working on the past year or so. Oh. Anybody have a quick way that I can get to the slide that I want to get to? What? Oh, awesome. Let's try. Okay. Well, let's start there. Okay, so sometimes you'll run into a flash chip or other chip where you don't have the documentation for it. So what I started to look at is, again, the electrical characteristics. If I started to notice there are certain patterns when you look at, let's say, the resistance between ground and the pins on the chip. And so I build a map like this of the different pins for this target. And I compare this to the ONFI standard, which is a sort of standard for compact flash interfaces. It gives you all these different footprints and what the common pin layouts are for it. So I started to compare the pattern that I see with patterns that should be on the footprint. So for instance, I would think that all of the I/O pins would have the same resistance. And here in this comparison, you can see that it doesn't quite match. So this is a 48-pin TSOP layout in black from the ONFI standard, and my electrical analysis in the orange. So here you see that ground and VCC might match, but what doesn't match is the I/O. In my case, some of them were not connected, or it seemed to be. So this particular footprint was for a 16-bit CFI standard. If I looked at the 8-bit CFI standard, then I started to have some very clear correlations. So we see that the resistance on the top right between the I/O pins kind of match each other. On the bottom left, we see that the not connects all match. The VSP3 is actually a Finder-specific pin, so it's optional, so that it's not connected is not strange. And this is sort of a way in which you could potentially re-document your footprint without actually having the documentation. So that can be quite useful. And that's basically it. I think at this point I hand off to Vadik to discuss DPCB. So, and then we might have to play around with the laptops here for a second. So if someone wants to come up and do a dance. Okay. So basically, DPCB is based on dgate, which is from Martin Schobert, and is used by Carcinal, Starbug, and all those to deal with reverse engineering of logic inside chips. So we were inspired by this, and we thought we could use a similar technique for reverse engineering PCBs. It's really quite simple at the moment. But hopefully in the future we'll be able to implement things such as visual analysis of the actual traces so that you could just look at the layers computationally and pull out the whole schematic. So what Vadik's going to do you want to explain it?
Yeah, well, I'm going to quickly reverse engineer this board that I have here, which is supposed to be an analog NLFO, a low frequency oscillator that we picked up at some music shop. So, 1 second. Oh, sounds like this. I'm going to take 2 photos. What's going on? Okay, I'm going to run a script to align the layers because they're aligned only vertically by the virtue of me bumping them against the F keys. So. Yeah, close enough. So what we can do with this program is basically now it's all manual. So what we can do is trace lines that you see here in this manner, more or less.
this particular case, this might be just a 2-layer board, but in some of the devices that I've seen, even though there are multiple layers, whenever a trace needs to go to whenever a trace needs to sort of go up or down a layer, and depending on the manufacturing style, you'll still have a full via, going between all the layers that you can still tap. So even though you might not have all of the layers, you can still do some reverse engineering just based on the vias and the traces that you see on the top and the bottom. And if you do want all the layers, there's a nice project, I can't remember who did it. I want to say BinNote. But they sent off a phone to China and paid €90, and they sand down all the layers for you and give you back pictures.
It was, yeah, it was Bunny.
It was what?
Bunny.
No, it wasn't
No,
Bunny.
no, it wasn't?
No, it was
okay.
BinNote or something. I can't remember. Yeah, so, and actually, if there's anyone that knows Chinese in the room, we really need your help, because I think this tool is only going to be useful once we translate it into Chinese. Yeah. So what are you doing? Are you loading it?
Okay, I'm going to cheat a little bit, and I'm not going to trace all the card in front of you.
It actually, this particular board we did as a first test in about 5 minutes over lunch while waiting for our food a while ago. So it's,
No, this actual the version I did at home within more or less 5 minutes to trace all of this, and about a minute to take the photos. So the useful thing that you get from here is the tracing of connections. You can click on one via, and it will show you every via and every line that is connected to it. So in this case, what we see is the ground plane.
yeah. Do you have anything else? Or-
Yeah, that's more or less it. There are ambitious plans to add image recognition to this software, so we can actually trace the lines by using some image forcing algorithm, and there was also
Yeah, there's two other areas that we're going into as well. One is thermal imaging. So the idea is to use a thermal camera, and if you have a thermal image video, let's say, of your over top of your PCB, then when you would apply solder heat to any particular via or trace, then you should see a heat signature through all of it. So that's one thing we're exploring. And then the other was, as I said, just there's one other where we want to take a web camera, which we're working on now, and typically, if you were to do this by hand, you would use a multimeter in beep mode, which is where when you put the two probes together, it goes beep. And so to do this by hand, you would place, a multimeter here, one probe here, and one probe there, and if it beeps, they're connected, and you would make note of this somewhere. So what I want to do instead is using a web camera and a multimeter over top of a PCB, just like Vadik had. As you move the probe around, when it hears a beep, then it knows, oh, this is the edges of the probe, so I place a dot here and a line to that dot there. So sort of, let's call it assisted manual tracing.
which is of course more useful when you have more than 2 layers and you can really see what's going on inside them, so you can trace them visually.
Yeah, so these are things that we're working on at the moment, and if anyone would like to help, we would be more than thrilled.
Besides the Chinese translation, what we need is actual users of this program, because the UI is just lacking. I'm just a programmer. I have no idea what to do with this stuff. So, thank you. Right.
So those are the tools that we went over. I have a few other human elements to show if we have time, which we do. Mm-hmm. Yeah. Oh my word. My computer has crashed, kind of. Okay, so maybe I take questions while I reboot my computer. Does anyone have questions about the tools? Okay, I'm just going to let the person with the microphone just find them. Who? The microphones are off, or?
No sound? Oh yes, there's sound. So
Hi.
what about you using X-rays? Because you would have maybe multi-layers if you have something of interest, because these music instruments are not so much fun. Would be much more fun to have maybe a 12-layer telecom board and re-engineer what they really do with the buses or something like that. And so you would need some X-rays, and maybe you need some computer tomographic pictures, so that you can, for example, say there's enough software for this medical stuff. So maybe you just change them so that they don't follow the veins and the muscles and stuff like that, but simply the traces. And so you can maybe get a net list of a board that you just put in such a X-ray machine.
Yeah, I agree with you. That's very interesting. And yeah, I would love to look at it. It takes some time, and perhaps someone who has some more experience with it should take it and do something like that. I have thought of getting a simple dental X-ray, but some people in the field have discouraged me, saying, no, that stuff is junk and it won't work. But I'm still not convinced. So yeah, it would be interesting to look at. You're absolutely right. It's a good avenue. So, any others specific to the tools? So you can ask me and I'll repeat it.
So in commercial PCB manufacture, they do electrical tests, which is an impedance signature of the track.
Yeah.
I wondered if you considered using that, because you don't need to work out what's connected. If you look at every wire.
Wait, okay, give him the microphone. Sorry.
Yeah, so in commercial PCB manufacture, the electrical test takes an impedance signature of each trace, and they use that to verify if all the boards are okay or if there are shorts.
Right.
So it means that every net has its own characteristic, and everywhere you search on that net, you get the same signature back. So I wonder if you would consider using that for this situation.
Yeah, that would be very interesting. I don't know if you need special equipment for that, but that would be very interesting.
Little.
If anyone has details about these particular devices, or I would love to work on them with you, if you guys have ideas. So maybe one more question before my PowerPoint is up. Okay.
Where would you like your tools to go?
Where would I like my tools to go? I had a sort of dream that artists would use these tools. That was actually such as the first example I gave, but I'm not sure. I think it's a very very unique case where an artist decides, oh, I'm going to reuse this cell phone or this device instead of going and building a new one or giving up on my project. So that is where I had hoped it would go, but I think it's much more useful for hackers. So when you say where to go, I have no idea. Like, China, please. Okay. Let's see. And it is here.
So I have another idea. What
Yeah.
about using high-frequency radar? So, for example, the stuff that are used in airports to find some bombs and stuff like that in people, maybe you can change the software so you can get a net list.
So you mean when I go through the TSA scanner, I sort of take a
For
PCB
example,
with me?
yeah, for example, you have to embed some evil stuff. So you have to, for example, say there's an ASIC that contains a very special military-grade explosive, and you have to further investigate it.
Exactly. Yeah. Then I mean, it was basically the hackers that were revolting against TSA. I mean, at least most of the hackers. So now they would become friends of TSA. So, yeah.
In terms of what he was just talking about with the airport scanners and trying to figure out the nets or the vias on the board, a woman called Jerry Ellsworth in Oregon is already doing this.
Oh, really?
If you, after a fashion, she has some YouTube videos on how to create your own, essentially airport scanner out of disused or out of dish network feed, and various other bits of hardware. You can get with me afterwards if you want.
Yeah,
I can give
if you can
links.
find me, that would be great. And why isn't Jerry here? That's what I want to know. Okay. Okay, so I just wanted to look at some other things that I noticed while looking at PCBs. So these are other areas that you might not think are interesting to look at, but actually looking at them, each arrangement and the way in which they're arranged and the way they look is important, or it gives some clues either to the developer or the manufacturing process. And in particular, some things you can look at are pads. So the pads you see there, one with a circle around it is not grounded, so it connects to something, and the one without is grounded in pretty much every case. Another thing to look at with pads is if you sort of put them, you make them reflect in the light, you can notice if there's an indentation on it. And if there's an indentation on the pad, it probably means that it was tested either manually or in a bed of nails tester. A bed of nails tester is this device that after they do the placement and the manufacturing and the board comes out and everything's soldered on, they'll pick it up and put it in this bed of nails where some of the nails are connected, and then they can run automated tests, so using JTAG or whatever. So if you see indentations, that might be interesting, especially if there's several of the pads in a cluster that are indented. Also, if you find solder left on a pad, that's almost always an indication that someone was testing those particular pads and indicates a debug interface of some sort. You also have like interesting patterns. So on the right here, this larger picture, all of these particular holes indicate some sort of RF area of the board, which is very common. You have non-conductive vias, and there's all sorts of other stuff as well. Missing components can be interesting to look at. So here we have what I think is probably an RJ45 connector missing. Here we have an SD card missing, a slot for an SD card just by the basis of the white outline that you see, which is for an SD card slot. Here in this case, which is a board that I showed a couple times after I took the flash chip off, I noticed this white marking underneath, and I talked to Felix Domke, who told me, oh yeah, that's a marking for a flash, CFI flash socket. And also the fact that there's only 10 pins on the left and 11 on the right also indicate. And doing that also like cut down the set of pins I actually needed to care about, and in fact made all my work almost useless. I can just go buy a socket and just throw it in there. So that's something to look at. Another thing that you might not think to look at is the edges of chips. So here you see JTAG is actually accessible on the edge of the actual microprocessor. So this can also be overlooked. But looking, I mean, this whole lecture I've discussed a lot of ghetto tools for looking at embedded devices. And on the one hand, it might be nice to have really expensive and nice tools, but you find some very beautiful results when you use ghetto methods. So in one case, I was desoldering a BGA chip, and I used a very horrible method. I just used a lighter because I was in a hurry and I wasn't at a lab. So I broke a lot of the solder pads, but using backlight behind the board, which I think this looks great, using backlight behind the board, I was able to sort of try to remap them. So if we zoom in a bit, we can see this is what a solder ball should look like if you properly remove the chip. But this, and what you would use that for is I would want to tap onto the solder point and then find a via on the outside, such as the other one, and see if they connect. And if they connect, and it's important, let's say it's a JTAG pin, then I would go to a device that I haven't destroyed, and then I would attach JTAG to it. So in this particular case with this target, I had a footprint, and I knew exactly which pins were JTAG. And the problem is that one of those pins, the ball was broken off, and there was no contact point left. So there was no way for me to map it out to the outside of the rest of the board. So we zoom in again. What I noticed is with the backlight, you can see that each point where each ball that is missing, you can still see a small like connection. In this particular case with this ball, the connection is going to the top right. In this particular case, it's going to full right. And with my pad, which is this one that I wanted, I didn't see it going anywhere, so I could take a guess. It's either the bottom left or the bottom right. And so in this case, I guessed the bottom left, which you can see here, and I exposed this, and I was actually able to successfully map it to the rest of the board and then go to another device and actually use that JTAG interface. So you might find all sorts of crazy solutions that are in themselves they're like what the fuck moment, you don't believe this works. So that's quite fun. So that's the tools and that's the techniques. So I just want to give a small argument for all the suits in the room, since there are a lot of them today. So there's a reason why my clients and probably your clients as well should encourage this type of development and disclosure of such tools. And the reason is, I'm just going to give a couple quick examples. So you probably remember from last year, Henrik presented on the Legic RFID card hack. So that is a card that was out in the market for a long time. It's used in critical infrastructure that if the public understood, they would be really scared, the fact that these cards are that easily hackable. And my point is we have academia doing research, security research. We have probably governments doing quality assurance testing. We have the organizations that build the tools themselves doing it. And yet it's still, we need this community element of the hackers who come in and just randomly, it's almost random, they find something here or there. It's a very important element. Another example is at Black Hat, H.D. Moore presented on the Wind River WDB debug port, which gives you full on-chip debugging of the embedded device. And Wind River was VxWorks was the most popular embedded operating system in 2007, and yet during that whole time, most of the developers left the WDB port open on UDP, so you could just sort of attach to the UDP port and just debug the device, dump the memory, etc. And if you look at the CERT listing for this particular bug, the list of vendors affected is like 50, the biggest names you can imagine in government organizations. And it took some hackers to come along and randomly check it and expose it. And that's somewhat amazing. And I'm not criticizing industry whatsoever. I'm saying we need all of these elements. So that's it. So to end, we do need some help as well. So with DPCV on some of the features that we discussed, if someone has some experience with visual computation, we are not fame whores whatsoever. We are not credit whores. We would happily give you all the credit. Just come help us. We want to just see our ideas come to fruition. And that's it. We also like to help. So if you have a target or you just want to learn or have some research, just contact us. You're welcome to stay at my house for 2 weeks. I will feed you, and we will do a bunch of interesting stuff. So that's it. I'd like to thank a bunch of people, Recurdy Labs for their help with the serial JTAG scanner and flash dumper, SRL Security Research Labs for help with DPCB, Christopher Chernovsky, Jorg, LaKernel, Zubab, TMB Inc., all these people for all of their valuable input. And these are all the links for the stuff you need. Okay, that's it. Any more questions? Any more questions? We have probably 5-10 minutes.
I've seen a number of Arduino-based approaches to do such kind of tools for reverse engineering. And
yeah, let me note.
The question is the hardware itself is rather limited. You said it's just a subset of the C language. Wouldn't it be an idea to, again, develop a card? What's mostly needed is GPIOs, right?
Yeah.
So wouldn't it be another approach to just build an interface card for a PC, just giving lots of GPIOs and having access to all the libraries and stuff we're used from our standard user land?
Someone says no?
Yeah,
I don't know.
I'd like to hear a reason, if not.
It's called an FPGA for sure, but...
No, I'm not talking USB here. I know that USB can't even do serial ports, but just like, I don't know, plug it to PCI, whatever. A chip which just gives shitloads of GPIOs.
You're absolutely right, and I know there are some projects that actually do make these types of platforms for you to do stuff with FPGAs or whatever. The advantage of using Arduinos is it's easy for everyone in this room that has not dealt with hardware to go tomorrow to the Arduino workshop and one day later be hacking an embedded device. That's the advantage, because the documentation is expansive. Your kids can do this, so why can't you? That's why I started this with. And that's specific to Arduino and not an FPGA. Your kids aren't going to pick up an FPGA and start. Well, maybe
I was thinking about buying a PCI card.
A PCI card.
Or whatever bus may be available on a standard PC.
It would be very interesting to see that. I also thought, like, why not just, yeah, like have 100 USB, like, anyway, I don't know. The reason Arduino is nice is because
C64 has GPIOs.
the reason Arduino is nice is because it's really simple, it's really stupid, well documented. A lot of people have them. That's it. Any other questions? Okay. So, ciao.